Thanks everybody for coming. My topic is I'm going to talk about graph algorithms that we've probably all heard of in a different way. My goal is to sort of take some ideas that probably we've all heard of and unite them into like this nice little idea that we can look at graph algorithms in a different way in the language of linear algebra. So the first thing that I want to do is talk about a couple of my references so that you know where this is coming from. There's a new book called the Handbook of Big Data. And chapter 12 is called Mining Large Graphs, and it was written by Gleick and Mahoney. And this is where I first heard about this idea. In this chapter, they talk about basically there are three broad categories of graph algorithms. There are graph algorithms that we can view as matrix vector products. There are also algorithms that are diffusion algorithms that look at a node and then sort of the region around that node in the graph. And then there are also graph algorithms where we only look at a node and its immediate neighbors. So this is the global kind of graph algorithm, if you want to think about it that way. And then the other good book to look at is called Graph Algorithms in the Language of Linear Algebra. I'm abbreviating. And this is by Kepner and Gilbert. So there's a whole book about this. And they go way beyond what I'm going to talk about today. But essentially, you can look at a whole host of graph algorithms as linear algebra problems. So the first thing that I want to do is, in order to view these algorithms as matrix vector products, we have to relax our idea of what is a matrix and what is a product. So in general, linear algebra, we talk about matrices and vectors over fields. So real numbers or complex numbers or any other kind of field. What we are going to use today are semirings. So I will say what that is. So a semiring is a set R. And this doesn't mean real numbers. It just means it's a set. The R stands for ring, I think, with operations plus and times. So I'm going to call this the addition operation and this the multiplication operation. It may not be the ones that we know of, but it could be. So one good example of a semi-ring, I'll put it over here, is the set of all non-negative real numbers. So you can think of it sort of as half of a ring. And these are the properties that it has to satisfy. So first, the addition operation needs to be commutative and associative. And there needs to be some sort of an identity, and we call it 0. And again, I'm going to put a circle around it because it could be the number 0, but it may not be. We also have the multiplication operation, which doesn't need to be commutative. In all of the cases I'm going to talk about today, I think it will be commutative, but it doesn't have to be for it to be a semi-ring. And there also needs to be an identity, and we call that 1. Again, it could be the number 1, it may not be. And then there's a distributive property. I won't write out what it is, but I will show you an example over here of what it looks like. And then also, we need to make this additional assumption that the operation of multiplication will annihilate the set R, which means that if I multiply anything by 0, I get 0. We don't need to assume that when we define rings and groups and things like that, or I guess rings, but we do here because it doesn't follow from these assumptions. So by 0. So if I multiply anything by 0, I get 0. So it's easy to see that this set together with addition and multiplication is a semi-ring because addition is commutative, it's associative, multiplication is associative. I have this identity. It is the number 0. It is the number 1 in this case. It's distributive. Right, so this works. And then if I multiply anything by 0, I get 0. So this is a pretty standard example. Another example is called the min plus semi-ring. And it may not surprise you that the two operations are minimum and addition. So the set that I'm going to talk about is all of the natural numbers, including 0, and also including infinity. Okay. And the two operations are min. This is the addition operation. So I take the minimum of two numbers. And then the multiplication operation is plus. So we can again sort of look at these properties and say, okay, I know that if I take the minimum of A and B, that's the same as the minimum of B and A. So it is commutative. It's associative as well. What is the identity in this case? We say that it's infinity, because if I take the minimum of anything and infinity, I get back that number that I started with. So this is the additive identity in this case. And then what is the multiplicative identity? It's 0, because we remember that in this semi-ring, we had addition, and the additive identity is 0. So now the multiplicative identity is 0. Any questions about any of that?
So you're telling me 0 is infinity and 1 is 0?
Yeah. So we have to be flexible with what we mean by adding and multiplying in order to make this work. There are other semi-rings. I may talk about the min times semi-ring, which is the same thing except I have multiplication here. And then happily, the multiplicative identity is 1 in that case. So, yeah.
Could you just remind me, what are we missing for a set to be a ring?
That's a good question. So why is this not a ring?
It's okay if you don't know too.
Does anybody know? I forget why.
Additive inverses?
Right. It's not a group, actually. Yeah, that's good. It doesn't have additive inverses.
Okay.
Thanks. So semi-rings are not groups. Okay. Any other questions about that? The first graph algorithm that I will talk about is PageRank. So if you took CS 515, we learned PageRank is a linear system that looks like this. And so the goal is we want to solve for x. P is a probability matrix, or it's a column stochastic matrix. All the columns add up to 1. V is also a column stochastic vector. And we can rewrite this, and I want to get it right. We can rewrite this as an eigenvalue problem. Okay, so if you just shift things around, these two things mean exactly the same thing. But now it looks something like AX equals X. So this matrix is guaranteed to have an eigenvalue that's 1. And we are interested in what the eigenvector is. So this is the PageRank problem. There are a lot of different ways to look at it. And also in 515, we learned the main algorithm that people use to solve this problem. It's called the power iteration. And what happens in the power iteration? We choose a vector x1, and it could be v. Some people will start with something other than v, but it turns out that v is a good choice. This is an iterative algorithm, which means I start with some guess as to what x is, and then I gradually refine that guess. So I come up with a series, or a sequence of vectors xk, where the next one is given by simply ax, right? And if I simplified this, it would look something like alpha px plus 1 minus alpha v. Does this look familiar? So what I want to stress is that when you solve this problem, all that you're doing is matrix vector products. And you're doing it over a semi-ring, although you probably haven't thought of that because the semi-ring is this one over here. Does that make sense? Any questions about that? OK. So now what I want to do is sort of open this up to more algorithms. Before I do that, what does it mean to multiply matrices and vectors over semi-rings? Well, it means the same thing as it did over fields. So I can have vectors that are over a semi-ring. I can define a matrix over semi-rings, right? And I can multiply matrices and vectors What does this mean? It means the same thing that it meant before. So element-wise, entry-wise, this is what we do when we do a matrix vector product. But now the only difference is we are flexible with what we mean by addition and what we mean by multiplication. OK. And then I also want to make sure that my graph notation is understandable. So a graph I will write as G. It has vertices. It has edges. We'll say that there are n vertices in the graph. These edges could be directed. They could be undirected. They could be weighted. They could be unweighted. Depends on the problem that we're looking at. OK. So any questions before I get to, I'm going to do shortest paths first. Do it over here. So the first graph problem that I asked was the PageRank problem. And now the problem is this. I'm going to talk about the single source shortest path problem, which is I pick one of the nodes, I call it S, that's the source node, and I want to know what is the minimum distance from S to every other node in the graph. So I'll write that down. What is the minimum distance from S to every other node, every other vertex? So I learned 2 algorithms to do this in my first algorithms class. One of them was Dijkstra, and the other one is Bellman-Ford. So in case it's been a while, I will remind you what the Bellman-Ford algorithm does to solve this problem. So this is a dynamic programming algorithm if you're a computer science major. If that doesn't mean anything to you, what we do is we are maintaining this array throughout the algorithm. And ignore the k for a moment here. So this is a vector. This is an array. It has n entries, 1 entry for every node. D stands for distance. So I am saying that D1 is the distance from S to the first node. D2 is the distance from S to the second node. The reason that there's a subscript k here is that this is also an iterative algorithm like PageRank. So I start with D1, and that's my first guess as to what D should be. And then as k gets bigger, I get closer to the actual answer, and Bellman-Ford will converge to the true D. So we initialize D1 to be this. So we say the distance from S to itself is 0. I know that without doing any work. And then also the distance from S to every other node, I know nothing about that yet, so I'm going to say that my best guess right now is infinity. So that's how I initialize S. This is how I initialize D. And now this is an iterative algorithm, like I said. So how many iterations do I need to do? At most, I need to do n minus 1 of them. I'll use k. It could be fewer, but just to be safe. For every iteration, what do? I look at every single edge in the graph. These edges, I should have mentioned, are directed edges. We can only go along the arrow in that direction, and they're also weighted. So every edge has a cost to it in every path. So for every edge, and we'll say with weight W, what do? I do this. I update, make that clear. I update the vector D like this. And this is the entire algorithm. So what do we do in every iteration? We look at every edge UV, and we say, how should I choose the distance from S to V now in this k+1 try? So what I do is I say, well, I already have a distance to V. Maybe that's my best guess. Or maybe I could use this edge to make an even shorter distance. I can find the distance to u and then add on the weight of this edge. So I'm not going to prove that this works, but this works, and it should be kind of intuitive as to why it works. So any questions about that? So when I think about this as a matrix vector product or a sequence of matrix vector products, I have to choose a semi-ring. And in this case, I will use the min plus semi-ring, which shouldn't be a huge surprise because the only two operations that I use in this algorithm are finding the minimum and adding, right? So I think I still have it up here. So I know what the identities are and everything like that. I will also define A, which I will call the adjacency matrix of the graph, but it's a little bit weirder than we might be used to. So the ijth entry of A should be the weight of the edge from I to j, if there is such an edge, or the number 0 if I equals j, or infinity otherwise. So if there's an edge between the two vertices, the ijth entry is going to be the weight of that edge. Otherwise, I throw in zeros and infinities everywhere else. So this is the same as what we would normally do for an adjacency matrix, because this is the multiplicative identity. Remember, this is 1 with a circle around it. So there are 1s along the diagonal. And then remember, this is 0 with a circle around it. So there are zeros everywhere where there isn't an edge. Does that make sense? So this is my adjacency matrix. And now what is the Bellman-Ford algorithm really doing? It's saying I have this, again, sequence of vectors x. And the first one, I initialize exactly the same as I did d over here. So the distance to s from s is 0, and the distance everywhere else, my guess, is infinity right now. And then all that we do is this. So this, I will argue, is the Bellman-Ford algorithm. OK, and remember, this matrix vector product is defined on this min plus semi-ring. So I will argue y in this space over here. So what does this mean? This means that the ith entry of x k plus 1 is going to be equal to the sum of A transpose ij times xj k, right? What does this mean? We could write it like that, and I will do that. So I'll do that now, I guess. So, but remember, the sum means minimum in this semi-ring, right? The minimum over all j. And then, yes, so A transpose ij is just AJI. Multiplication we defined as this, it's plus, and then we get xjk. So I'll write this a little bit better. So what does this mean? It's the minimum over all xjk, or sorry, over all j of xjk plus, well, it's the weight of this edge from j to I. If there isn't such an edge, then it's going to be infinity. So that obviously won't be the minimum. So I hope that you can stare at this and see that this is doing the exact same thing as the Bellman-Ford algorithm. So essentially, what I do is I look at every edge in the graph, and what we say is we relax every edge to get a shorter path. Are there any questions about any of that?
What is the convergence criterion?
Well, we could do this n minus 1 times, and then I will guarantee you that it converges. Or if you notice that x doesn't change after you do an iteration, then you know that you're done. You look at every edge and you say, I can't get any shorter than this, so you're done. Any other questions?
So one matvec is equivalent to one outer for loop. Yeah, okay. So for a particular value of k, run the inner for loop to its completion. That equals one matvec.
Yes.
Cool.
So this right here is one matrix vector product. Cool. So do you want me to do an example of this, or should I do connected components now? Probably connected components.
I have one quick question.